To predict exactly how rigid materials, like this thick steel beam, warp and bend under extreme forces, we can't rely on physical intuition alone. We rely on a specific mathematical representation: four distinct, overlapping cubic curves, known as Hermite polynomials, constrained between two fixed structural boundaries. Notice where these curves peak and cross the zero line. Their exact shapes are dictated by physical constraints. To understand finite element analysis for beams, we must examine why structural physics mathematically requires these exact four cubic curves. Understanding the derivation of these equations allows us to simulate any complex structural bending problem in modern engineering. Let's start with the simplest form of structural analysis, the one-dimensional bar element. This diagram illustrates a standard bar element, requiring exactly 1 degree of freedom per node to track linear stretching or compressing. Watch when a vertical load strikes the center, the geometry rigidly fails to warp or bow. The one-dimensional model cannot represent bending. To calculate these transverse loads and their resulting moments, we move to the Euler-Bernoulli beam theory. Under this theory, each node requires two specific degrees of freedom: the lateral deflection, which measures vertical movement, and the rotational slope, which measures the bending angle. Since the standard beam element spans two nodes, and each node requires two parameters, the total system complexity is exactly 4 degrees of freedom. Introducing a transverse load forces a necessary shift from simple linear models directly into a more complex 4 degrees of freedom architecture. This presents a clear mechanical challenge. We must represent a continuous perving geometry across an entire beam using only 4 discrete pieces of nodal data. We use this generic 4-term polynomial to link our discrete data nodes to a continuous curve. The 4 unknown terms in this equation, A0 through A3, map directly to the 4 data slots located at the nodes. A simpler equation, like a quadratic, lacks the variables to capture the bending shape. A higher-order equation, like a quartic, would leave us with more unknowns than we can solve with 4 data points. A cubic polynomial is the specific mathematical requirement for an element with exactly 4 degrees of freedom. The physical constraints of the beam's bending dictate the exact geometric complexity of the mathematical equation we must use. To solve the system, we separate the physical geometry from the unknown variables. Watch as the cubic equation splits into a vector matrix format: a row vector, h, multiplied by a column vector, a. The row vector h contains geometric variables representing physical positions. The column vector a holds the unknown coefficients we must find. Because 2 of our degrees of freedom measure rotational slope, we take the first derivative of this polynomial vector system to calculate those angles. Isolating the unknown coefficients into a dedicated vector transforms a structural physics problem into a standard linear algebra equation. We solve for these coefficients by applying local element coordinates. We establish local coordinates on the left: node 1 at x equals 0, node 2 at x equals L. Substituting 0 for x collapses the terms, isolating our initial constants. Next, substituting length L generates new constraints defined by L, L squared, and L cubed. Setting the boundaries at 0 and L is a standard efficiency and finite element analysis. Global physical coordinates are typically reserved for specialized analyses. These specific fixed boundary conditions serve to firmly anchor our abstract polynomial right to the physical dimensions of the beam's endpoints. We now have a complete system of equations, ready to be solved. These substitution results organize into a 4x4 transformation matrix representing the element's geometry. We invert this matrix to solve for the column vector A in terms of the nodal degrees of freedom. Multiplying this inverted matrix back against our original row vector H yields the final interpolation equations. The algebraic output manifests as the 4 distinct cubic shape functions we saw earlier. This entire derivation process is exactly what allows us to translate discrete nodal values into a continuous physical bending shape. We can now examine how each shape function contributes to the physical geometry. This is a plot of function n1. It starts at a full vertical value of 1 with a perfectly flat initial slope. It then drops to 0 at the opposite end and flattens out again. It starts with a vertical value of 0, but a steep slope of 1. before returning to a zero slope at the far boundary. This corresponds to the isolated rotational slope of the first node with no vertical displacement. Each curve represents a state where exactly one nodal movement is active, while all others are constrained. Functions m3 and n4 act as the mathematical mirrors of the first two curves, governing the lateral and rotational movements of the second node. Viewing all four curves together reveals the physical rule governing their design. A shape function must equal 1 at its target degree of freedom and 0 at all others. Watch the scan. Each curve achieves exactly 1 at its designated parameter, returning 0 elsewhere. Verifying this 1 and 0 condition is a mandatory diagnostic for any valid shape function, regardless of element complexity. By applying Euler-Bernoulli principles to solve our polynomial system, we've moved from a simple bar element to precise curves enabling true bending simulation. These cubic interpolation functions provide the mathematical engine required to assemble the element stiffness matrix, the ultimate goal of finite element analysis.